the U.S. Technical Guild Presentations Day. We are very excited to say that our speaker today, Yaniv Nahoum, is live from our studios in Tel Aviv. I'm going to allow him the opportunity to introduce himself, but as a reminder, all of our sessions are recorded. If you have an issue with being part of a recorded session, now is your opportunity to leave. So without further ado, I will go ahead and start the recording session and allow Yaniv to start his presentation.
This meeting is being recorded.
Thank you, Rob, and hello, everyone. Thank you for joining me on this session on Dockerizing your JVM apps. For those of you who don't know me, my name is Yaniv Nahoum. I've been with the company for almost 10 years, I think. I'm a software developer, obviously, but I'm also a technical coach, which means that I work with development groups throughout the development lifecycle, from architecture through testing, obviously coding, deployment, and anything in between, from design reviews to tweaking your IDE. I put a very strong emphasis on productivity and engineering practices. So that's me in a nutshell. This talk about Dockerizing your JVM apps is mostly meant for developers and DevOps engineers. And I hope that by the end of the talk you'll agree with me that in order to get optimal results, we need the cooperation of the two, because developers have some of the information and the knowledge. DevOps engineers have another part, very important part of the information, and we need the two to work together in order to reach the results that we're shooting for. So what's on the menu for today? So we'll only tackle three things. First one is reducing the image size. We're talking about Docker images, the size of the images, and the build time. We want to reduce those. We're going to be talking about increasing our image security, which is a very important topic. And the third thing we're going to be talking about is tuning the JVM to our needs. Most of the points that we're going to be tackling have nothing to do with the Java or the JVM, but I do want to address that topic in the very last point. So we're going to jump right in with talk about reducing image size. So if you're not Docker savvy, don't worry. I think you'll be able to follow along. This is a basic Docker file. We can see the from line, the from instruction, which instructs Docker to build this image, starting from a base image. So in this case, it's OpenJDK 11. We then instruct Docker to copy a precompiled jar on our or a pre-built jar on our host to the root of the image, and we're going to rename it application.jar. We used Maven here, so it's under the target directory. And then last thing, we have the entry point, which is basically the command that's going to run when we start the container based on this image. So let's see what that looks like. And just a quick word about the application that I'm going to use here as a demo. So it's a very basic Spring Boot application. I use Spring Boot since it's so very common in the JVM world. And what it does, well, it's a web application, so it starts an embedded web server, Tomcat, but also it prints some very basic info regarding the environment that it finds. We'll need that for later. Don't worry about that now. So let's go ahead and build our first image. So I'm going to run docker build. Take a look here. Docker build. I'm going to tag the image demo:1. Usually, Docker uses a default name for the Docker file, which is Docker file. But since for this demo I have many Docker files, I'm going to be specific, and I'm going to use the -f switch. So -f docker 01 blah blah blah. That's the name of the file, and then the dot here is the context. I'm going to talk later about the context, but for now, I'll just say that the context is anything in the host that can be used to build our image. So that's everything, the current directory. Go ahead and build this, and that's it. Okay, let's move on. See if we can do something better. What we can do better is we can take a smaller image. I'll show you in a bit what are the differences, but for now, just take a look at this line here. This from line, I changed that. So now I'm going to use, instead of OpenJDK 11, I'm going to use an Alpine version. Okay, this is from the Adopt OpenJDK repo. Alpine, as most of you probably know, is a very, very small Linux distro, and this Java image is JVM image is based on Alpine. So the rest is basically the same, and we're going to build that in a sec. But if you know what I'm doing here, I'm taking a pre-built jar, copying it, and then I'm running it. So I actually don't need a JDK. I can do the exact same thing with a JRE. And the JRE is significantly smaller. We'll see in a bit. So let's build these two images. Let's go ahead and build number 2. And we'll go ahead and build number 3 too. There we go. What I'm going to do now is I'm going to look at the sizes of these images. So let's take a look. We have number 1 with 665 megabytes over here, and then number 2 with 359, much better. But look at the JRE with Alpine. It's 166 megabytes. That's a huge difference. So basically what we can see is we can use a wide variety of base images. And if we're talking about the JDK, we can start with 706 megabytes up here down to 253 megabytes over here. And if we move on to the JRE, we can start with 506 and down to 147. And this image, this exact image that we see here, 147, is what I used in the last image. So huge differences. Choose your base image wisely. It makes a very big difference. Next thing that we'll talk about is minimizing the context. So as I mentioned before, the context is basically anything on the host that Docker can use to build the image. Not sure if all of you know, but Docker has a client-server architecture. So basically, when you run Docker commands, when I run the Docker build, I use the Docker client. It contacts the Docker daemon, the server, that is usually local on my machine as well, just like the client, but it can be remote. It can be a remote server. And then all this context has to be sent to the server. So one thing we'd like to do is minimize this context. In the past versions of Docker, if you specified dot and you had a lot of files in the current folder, it would just send the whole thing. I don't remember exactly in what version this happened, but in the latest versions, I noticed that this has been drastically improved. It now actually takes a look at the Docker file and sees what files it needs, and it sends only those. So that's a huge improvement. But still, we want to minimize the context for security reasons. if you don't minimize the context and if you don't specify exactly what you want to copy, when you copy a folder, there is a chance that you'll leak secrets from your repo into the image. And this image can be, sometimes you even push it to a remote repository that may be public. And you can find things like this, like that online. So easiest way to minimize the context is to use a .dockerignore file. And I recommend this pattern. First, I ignore everything, and then I start adding back exactly what I need. So this is a great pattern, and I encourage you to use it. Let's move on. We'll talk about using non-root images. So when the default for Docker, the default user for Docker is root. So unless we actively do something, we're running all our images with root, which is it's a security risk. It adds more surface exposure. We don't need this risk. So it's very easy to create non-root images. Here's an example. Let's take a look here. Let's take a look at these commands here. The first run command. So this is Alpine. I add a group. I then add a user with a name that I decided on in advance, and then I change the owner of my jar, and then I use this instruction user, which means that this command in the entry point and any subsequent run or CMD instructions will be run with this specific user. Let's see what this looks like and see the differences between an image with a root user and an image with a non-root user. So let's start with this. We'll start with this Docker file, the one that we saw before. I'm going to docker exec into this. Sorry about that. I'm going to docker exec into this image. Just a second. Here we go. Okay, I ran the image that we built before, the number 3, and I have a shell into this container that I created from this image. And let's see, who am I? I'm root. That's not surprising. That's the default user. What else can we see here? Let's see. Who owns application.jar? Also root. Let's see who's running the process. Process number 1, root. Okay. So let's exit. No need for Docker stop here. Okay, and what I'll do now is I'm gonna take the image that I showed you before, this one here, the non-root one, and let's go ahead and build it. Perfect. And let's run it and then docker exec into it, just like we did for image 3. And let's do the same thing. So now I can see that I'm demo user. I'm no longer root. I can see that application.jar belongs to demo user. If I run ps-cf, I'll see that demo user is running the process. And if I try to do stuff like, I'm on Alpine, so I'm going to try to add curl here. So I'm going to get permission denied, which is great. It's what we were shooting for. So Nonroot Images, very highly recommended, easy to do. There's no reason not to use them. And this is one of the, I think, most common pitfalls that I run into when working with teams. And it's really a shame because it's so easy to fix. Let's talk about minimizing the number of layers. So what are these layers? Every time we run, add, and copy instructions, they create additional layers in our image, and they increase the image size. So we want to minimize the number of layers. We'll see later why we do need these layers sometimes to be distinct. But let's take a look at this example here. So we have three run instructions that add the first one adds the group, then we add the user, then we change the owner of application.jar. We can very easily combine them into one instruction, just like you do in Bash or in other shells. We just use the ampersand and then concatenate these commands. Simple and effective. This decreases the image size. Let's talk about using multistage builds. So what are these multistage builds? Well, sometimes when we have complex builds, we need to do things like first compile and build our artifacts. In this case, I have a Maven application, Maven Java application. I run Maven clean install. I get a jar. So that's my first step. And then I move on to the second step, and I copy that jar, and then I define my entry point. Sort of like we saw before, only here I'm also compiling. Now if we think about this for a second, which image am I using to run my application? I'm using the one up here, this one. So I'm using an image that has the JDK because I need it to compile, and Maven, and I'm using that to run my image. That's really not what I wanted to achieve. I wanted a very thin image to run my application, but I needed other tools to build it. So multistage builds help us in that exact scenario. Take a look at this. What changed here is highlighted. So what we have here is we labeled the first from with a name as builder, and then in the second stage we added a from. So we have a new base image, and in the copy instruction that we see down here, we can actually pick and choose what we want to copy from the first stage to the second and final stage. So this is exactly as we would do if we needed to do it sort of by hand. We'd create the first image, we'd create a container from it, we'd copy it to the host, and then create the second image, and from the host copy stuff into the new image. So this is a very simple and effective way of doing exactly that. We'll use that later on. So these are called multi-stage builds. Again, very effective. This is not all you can do with the multi-stage builds. There are other things. Like for example, you can when you build your image, you can pass the -- target switch, which enables you to tell Docker build up until this stage. So stop at this stage. Don't go all the way. And then for different environments, we can have different images, because maybe later on we have stages that add additional tools that we want only for dev, but we don't want for prod. So very, very strong tool, multi-stage builds. Another crucial topic, leverage build cache. So let me try to explain how the Docker cache builds, how the Docker cache works. Sorry. So Docker, when it runs into an instruction, any instruction, it first checks if it already has an image, and maybe an intermediate image that correlates to this instruction. If it does, it uses it. This is the cache. If it doesn't, it just executes the instruction. So for copy and for add, we're not going to be talking about add, but for copy for now, it compares the checksum. What does that mean? It means that if we have a file, it doesn't really matter when it was created or when it was modified. The only thing that matters is the contents and the metadata of this file. If those changed, then Docker will invalidate that cache and do the instruction again. If it doesn't, if it hasn't changed, checksum is the same. It uses the cache. This is very, very effective, and we'll see how Docker uses it in a bit. Take a look at this Docker file. It has to do with something that Spring Boot enables us to do very, very easily. So what we're doing here in this first part is we're basically taking our jar and we're exploding it. This is what this line here does. Over here, this extract. So we're taking our application jar and we're running it, but with the -d jar mode equals layers tool. Okay, and passing this argument extract. And what happens is that our application is extracted into layers. We get by default 4 layers. We get our dependencies, we get our release dependencies, that is. We get a layer that has to do with the Spring Boot loader. We get snapshot dependencies, and then we get our own application code. And we can use that to leverage the build cache. How do we do that? As you can see from here, I put the copy instructions one after the other from the layer that changes the least frequently to the layer that changes the most frequently. And why is that? That's because the Docker cache works in like this. Once there's a cache bust, so once the cache is invalidated, all the instructions from there down will not use the cache. Okay, so we're interested in getting the cache to be invalidated as late as possible. So this is why we order the layers this way, because the dependencies, they don't change that much. Definitely not the Spring Boot loader. Snapshot dependencies, yeah, they definitely change more often. And the application code, our code, changes very often. So that's why it's last. Okay? Let's see this in action. So going back here, this is a layered Docker file. In this one here, I also have what I need for the Nonroot image. And note that I added all this stuff before copying. Again, because this stuff never changes. So I want to push it to the top. And I want to keep anything that changes frequently towards the bottom. So that's the logic over there. So what we're going to do here, first let me clean the cache. Okay. Hold on. Try that again. Okay, I'm going to build number 6. There we go. And now, what I'm going to do is I'm going to change. I'm going to go to my application over here. I'm going to make a change. Let's add for version. I'm going to go here. I'm going to run maven clean install. I'm going to skip tests for now. And I'm going to build it again. I'm going to build the same image now. And what I want you to note is this. We can see that most of it was taken from the cache, but the application .jar obviously changed. So we can see that this was not taken from the cache. And since there was a cache bust here, run was not taken from the cache either. Okay, let me go back for a second. Okay, so this, obviously, this line was not taken from the cache because application.jar had a different checksum than what we previously had, and then that made this one invalidated this one as well. But now we have a new image. So for the new image, we can keep on taking things from the cache, and that's exactly what Docker did. So you can see this cached, and then all the way, look at these three layers, these three over here, all taken from the cache, okay, until the last one, which is our own code. So this greatly improves build times, and it also greatly improves the time that it takes to push these repos, these images to the remote repo, which is something that we need to do because almost always we'll be deploying later on Kubernetes. So it needs to pull that image from somewhere, and it does so from the remote repo. So this has a pretty big effect on build times. So that's the build cache, and that's how we can take advantage of the layers. If you're not working with Spring Boot and you don't have these automatic layers, obviously you can make them yourself. But without doubt, Spring Boot comes really in handy here. I mean, it's very, very easy to get that done. Okay, next one up. Handling signals. This is another very common pitfall. I see this done wrong a lot, and I think it has very grave implications. And I think you'll agree with me once I explain exactly what's happening here. So basically, any process that we run needs to be able to handle signals. The same goes for a process inside Docker. So when we run Docker stop, or if we're on Kubernetes, when it kills or deletes that pod, it sends it a signal, and following this signal, which is usually a sig term, so it's a kill -15. What happens is, or what should happen, is a graceful shutdown, because this app very likely has dozens of connections to a database, or threads running, or who knows what, but all that has to come down very gracefully. Otherwise, we'll leave hanging connections. Our database will complain. We can wreak a lot of havoc if we don't do that. And what we see here is something that is very common. It's an entry point that runs a script, and this is a script here on the right. The script, what it does, it runs an application, a Java application with a jar. Now, obviously, usually this script will be a bit more complex, but at the end of the day, that's what it will do. It'll add other variables. Maybe it will have an if or else or stuff like that, but the bottom line is that it will start a Java application. Now let's take a look at something like that and see what happens when we run code like this. So we're talking about this. and what we saw before. Sorry. And this. So let's go ahead and build this image, and then we'll run it. Okay, so I built it. Now I'm going to run it. And I'm going to exec into it. Great. And what I want to show you is something very important. Look who's process number 1 here, because this is critical. Process number 1 is our script, but our Java application that needs to handle all the signals is process number 8. Okay, and it can't handle signals if it's process number 8, because process number 1 in Docker is a special process. All the signals are funneled to process number 1. So this will never work, and to prove it, I'm going to exit this shell, and now I'm going to time. I'm going to time the Docker stop command. Okay, I'm going to stop this. So what's happening now is Docker sent a sig term to demo 7. It's going to wait up to 10 seconds, has a timeout, and after 10 seconds, it's going to send a kill -9. So killing it very violently. And you can see that it took just over 10 seconds. Now, how do you fix that? It's so simple. You just add exec over here. So exec before my command. I'm going to do the exact same thing. I'm going to build this. Great. I'm going to run this image, and I'm going to exec into it. ps-ef. And now I'm process number 1. Let's see what happens now when I send a Docker stop. Let's see how much time it takes now. It's almost immediate. It's 400 milli. Okay, so it's a huge difference. And obviously, it's not only the time. It's not only those 10 seconds. What's critical here is that I enabled the graceful shutdown. So I saw a lot of problems for many teams that didn't implement this correctly, and they didn't understand why they're getting problems with their database and problems with other connections that were left hanging. So this is a reason. So let's move on to the last tip for today: configuring the JVM. So I want to start with a quick question. Feel free to answer if you want. If not, we'll see later on what the answer is. But take a look at this command. I'm running, basically creating a container off of the OpenJDK 11 Alpine. But what's interesting here is that I'm specifying 1 gigabyte of memory and 2 CPUs. And I ask you, what is the max heap size here? And which garbage collector will be chosen for me? And what happens if I change it to 2 gigabytes? Will that change anything? How about if I change it to 1 CPU? Will that change anything? So let's try to answer those questions. So I'm going to start off with 2 gigabyte and 2 CPUs. What I'm doing here is I'm running the command that you saw before, but I'm also running a shell and passing it with the -c. I'm passing the command Java with the print flags final switch, and then I'm grepping only the lines that I want to show you, which basically contains the information that we talked about. So 2 GB of memory, 2 CPUs. What I see here is that I'm getting 25% of that as max heap size. That's what I see over here. I'm using the G1 GC, the garbage first garbage collector. And there's something called max RAM percentage, and it's at 25%. That's its default. Value. Okay. So what happens if I now change that to 1 CPU? So memory is still the same, but take a look here. I'm not running G1 GC anymore. I'm now running the serial GC, just by having 1 CPU. And then what happens if I go back to 2 CPUs, but 1 GB of memory? So again, I have, well, obviously it's less, but it's still 25%. 25%. And of all the memory that I have, because I have 1 GB, and then I'm using serial GC again. Okay, so what's happening here? Let me try to explain. So basically there are 2 classes of JVMs. There's a server class, and there's a client class. And if it's a server class machine, then we get by default the G1 GC garbage collector. And if it's and some other stuff that I'm not going to go into now. If it's the client class machine, then I'm going to get the serial GC. And in general, a server class configuration is maybe a little slower to start up, but has more aggressive optimizations during runtime. And the client class machine is the exact opposite. So it usually starts up a bit faster, but it has less aggressive runtime optimizations. So you don't have to know all this by heart, obviously. But what I think you will agree with me is that you do have to configure your JVM the way you want it. Because in different environments, we sometimes have different memory limits, different CPU limits, especially if we're working with Kubernetes. And we want to be able to have at least some of the stuff fixed. Like, for example, we want to be sure that we're always using the garbage first garbage collector. That may be one thing that we want to use. Another thing is that we saw that by default we're using 25% of our RAM, which is pretty low. I recommend to use anywhere between 50 and 70% of the RAM. We'll soon see how best to do that, to achieve that. But we always want to leave space for native memory. That's for the meta space that is used in JDK 8 and above, which is what we're using. And so metaspace has class definitions. It has a common pool. There are obviously common strings, the string pool, and we need to leave space for direct buffers, byte buffers. We need to leave space for thread stacks, which are by default 1 megabyte per thread. So that can really add up. So that's why we'll never go to 100%, and I recommend not higher than 70%. But obviously it's trial and error. So let's take a look at how we can actually configure these things. So configuring that percentage is done with this flag, the max RAM percentage, and here I also configure the garbage first garbage collector. But the way I did it here is I hard-coded my configuration into the Docker file, which is actually not a very good way to do it, because it doesn't allow me to change my configuration per environment, which is something that I very, very often need to do. Not necessarily with these two flags, but other flags sometimes need to vary. It may even be a proxy configuration, proxy.host and proxy.port, stuff like that. So what I very often see is this. I see Docker files that define some environment variable. A lot of times it's called JavaOps, but it can be anything. And then it even has a default value here. And it's embedded into the entry point command. I followed my own advice and used exec here. It's important. Let's see what happens when we use this type of syntax. So we're going to go back here and we're going to take a look at this Docker file. Okay, let's build it. Great. And now let's run it. So I'm going to run this, and I'm not going to run this in daemon mode. I'm going to run it in the foreground. So we're going to see, if you remember at the beginning of the talk, I talked about my command line runner. Let me just show you it quickly. We'll see it here. So the command line runner will run, and it will spit out some information, and we can understand what's going on. So here we go. It's coming up, and okay. So we said max RAM percentage is at 75% of 512 megabyte, and indeed, we can see that the JVM heap is 16 megabytes now, but out of a max of 371. So we definitely achieved what we were after, and we didn't embed it. We didn't hard code it into the image, which is another thing that we were after, because I can pass with -e. I can pass the environment variable and pass whichever value I want. But there's absolutely no use in doing it this way for a very simple reason. And the reason is there's already a built-in environment variable that the JVM looks up for these exact things. Let's take a look. Let's go back to this image, number 3. Remember, it has no, as you can see, it has no reference to any environment variable. Let me just leave this. Let's build image 3 again. There we go. And let's run it. Okay. Take a look at this command here. So what I'm doing is, again, I'm limiting my memory to 512 megabyte, 2 CPUs. I'm passing a variable just like I did before. It's not mentioned here. It's called Java Tool Options. Java Tool Options is a predefined environment variable that the JVM looks up. Let's run this. So the first thing I see is that the JVM prints out picked up Java Tool Options with my value. And then I can also see that it actually did work. So 371 is 75% of my half a gigabyte. So that is definitely the best way to pass JVM flags to the JVM. And we can take a look here, and see that obviously most of us will be working with Kubernetes. So in Kubernetes, it's super simple to add environment variables to our containers, and this is what it looks like. So in yellow, we can see the Java tool options. I passed a few additional. I passed here a few additional flags. I used the max RAM percentage. I also passed the max metaspace size because it's unlimited by default, and max direct memory size for byte buffers. Heap dump on out of memory error, always good to pass because we want a heap dump should we get an out of memory error. And then what we talked about before, the G1 GC and string dedupe. We're not going to be talking about that now. But what's important to note here is that just by specifying this environment variable, I'm configuring my JVM. Very easy to do and very effective. And now I can limit the size or the amount of my RAM in one place, because what I see teams doing is trying to sync between the famous minus XMX and minus XMS, which is the maximum and minimum of the JVM, and the Kubernetes requests and limits. So no need for that. Just define your percentage and limit it in one place, which is the right place over here. Okay, that's how you should limit the memory to your pods. And obviously the CPU also gets passed on to your containers correctly. Great. So let's recap and talk about what I want you to leave this talk with. So first thing, small image. Use small image. Be very aware of your base image. Use the smallest image possible. Choose a JRE if you can, and not a JDK. And for other runtimes, choose something that is based on Alpine. It's usually smaller and very well maintained, by the way. Small context. We talked about the context. Context size is no longer such a big deal because in the later versions of Docker, it's been optimized, and it picks and chooses only to send to the Docker daemon the files that we need. But still, we're more error prone if we don't limit our context. We're running the risk of leaking secrets. So use a Docker ignore file. It's good practice. Use non-privileged containers, Nonroot. It's easy to do. It's more secure, and you have nothing to lose here. Minimize those layers. Remember, we talked about the run and copy instructions that create layers. If you have a few commands that you need to run and they're logically one unit, then combine them into one instruction. You'll decrease your build images and the build time. Use multi-stage builds. We talked about that. When you have a complex build, use a multi-stage to end up with a final image that is exactly what you want, and don't settle for an image that contains a whole lot of tools that you need only in the intermediate stages. Multi-stage builds will get you what you need. Leverage the build cache. We saw how you can take advantage of different layers and ordering the layers correctly, putting the ones that change less frequently on top and pushing those that change frequently all the way down to the bottom, so that when they do get invalidated and invalidate all the instructions below them, there won't be a lot of them. So use the build cache. It also really has a great effect on decreasing build times and upload times. Handling signals. I stress that a lot. I hope the message got through. We need to be able to handle signals correctly, so that we can, especially so we can shut down gracefully and not leave any hanging resources. This is easily done either by using exec if we have a script, or just entry point with our command. That also works. If you're not using, if you're not starting an application or a process that knows how to handle signals, I think Node is one of them that doesn't know how to do it. So usually you need to wrap it with an init process like Tiny. I'm sure you can Google this stuff and find the answers. But if you're aware of the fact that you need to handle signals, that'll get you 90% of the way. And last but not least, tune your JVM. Don't accept these defaults that have to do with how much memory I have, how many CPUs do I have. If there are things that you would like to be fixed for all environments, then take the initiative and add those flags. Besides, there are other flags that should always be added, like the ones we saw about the heap dump, and others may be garbage collector, and of course limiting your percentage of heap size, and then configuring the heap size in via Docker or via Kubernetes and the resources and limits. That's all I have, guys. So I'd be glad to take any questions now. I think we have questions in the chat. Rob, could you help me out here?
Most certainly. Just as a reminder, everyone has been muted. Make sure you unmute yourself before asking your question.
If there are questions in the chat, maybe we can someone can read them.
There actually aren't any technical questions. There were some issues regarding visibility and sound, but no technical questions.
Okay. Okay, guys. So don't be shy. I'm sure some things came up. I mean, I don't believe that everything was crystal clear here to everyone.
Hi, this is Sammy Kulkarni.
Hi.
I was wondering if you could elaborate a bit further about using init, the tiny and init that you mentioned, when to use it versus when to use the exec.
Sure. Well, basically, it's not either or. The problem is that some processes just do not know how to handle these signals. So there are additional loopholes that you need to jump through, loops that you need to jump through. So one way of getting this done is using a small wrapper. I think the most famous one is Tiny. There's another one called dumb init that I know of, and basically they just wrap your process with this additional functionality of handling signals, and they communicate with your process. So I mean, I haven't used that a lot because I'm more in the JVM world, and Java's got you covered on that front. But I've definitely seen Node images that use that. So if you're running them with Docker, you don't even have to do that because Docker has a switch ---- init, so you can run your image with ---- init. And what it does is it actually uses Tiny to wrap your the process that you put in your entry point. But if you're using Kubernetes, I actually checked today, they don't have an answer for that. So you're going to have to embed Tiny or dumb init or whatever you choose in your entry point. I hope that answers your question.
Yeah, thank you so much.
Sure.
It was a very enlightening topic.
I'm glad. More question, guys.
Yaniv, it's Yossi Yari. Can you hear me?
Hey, Yossi, yeah, sure.
Hi. When you ran, I think, the 6th Docker script, you had, and you showed the caching, one of the stages that was earlier on was not cached because the binary for the jar was different, but then it continued to use the cache. I didn't understand why that didn't break the chain.
Ah, yes, that happened thanks to multi-stage builds. So if I had a single, so in that case, I could have used actually a single base image, and I could have, because I didn't need a JDK there, I could have actually used a JARE and ran all the commands straight. But that would indeed bust the cache and then invalidate the cache for all commands. But since after the command that you saw that was invalidated, I started a new multi-stage, a new stage in my multi-stage build. And since I started in a new stage,
can you show that again?
Sure. Since I started a new stage, the cache wasn't invalidated. So this was the first part, and this part got invalidated. But then from here, it used the cache again, and it got invalidated only down here again. So it's per stage. Does that answer your question?
Show that again, because it didn't switch. The view didn't switch.
Sure. Let me
Okay.
close this. Okay. So again, this one got invalidated, and it invalidated the one below it. But then from here we have a new stage. So all this was cached, and it got invalidated only here. It's a good question.
So every from is a new stage?
Exactly.
In the
Exactly. Every from is a new stage. There's another way that we can use multi-stage builds, and that we can use copy from, and then we don't have to reference our stage here. We can actually reference an image, like a public image, and copy stuff from there. So this is one way of doing it, maybe the more common way. But another one is copying from any public image. That also works.
Oh.
But when you see multiple froms, you know this is a multi-stage build.
Okay. So the copy from also a new stage, you know.
No. The copy is part. We have two stages here, right? Because we have two froms. So this is the first stage. And the rest is the second stage. And what we're doing here is we're saying copy from builder, because we labeled the first stage as builder. And we're saying copy from this image, copy, and then we're even changing the owner as we do it, because here we used root, and here we're no longer root, we're demo user. So we're saying copy from builder, change the owner on the way, and copy dependencies to the current directory, which is our working directory.
Thanks for the explanation.
Sure.
Hi, this is Sammy again. I have two questions actually.
Sure.
Hello. The first one is regarding just generally, this is a way in which in the same Docker file you're doing the building, the application building as well as the packaging. Are there any pros and cons or best practices related to building it in an external DevOps pipeline, the different phases versus in a Docker file? That's one question. I mean, maybe I'll ask the next one later.
Okay. Well, it's a good question. It really depends There are pros and cons in building it inside a Docker image. One of which is a very clean and reproducible environment. Whereas if you have a machine that has things cached there, and maybe people SSH into the machine and can change things there, so they can maybe mess up some of the stuff that can affect the build. That can happen if you start with a clean image every time. But it also has its cons, because it's harder to cache, especially like if you're using Maven. Then you're downloading stuff. Next time you won't have it. You won't have that stuff there. It'll be harder to optimize that build. Whereas if you have a machine, a VM, or any agent that you're reusing for your builds, you're covered there. So there are pros and cons. There are other reasons to use multi-stage builds. This is not the only reason. There are more stuff that there are more situations in which you would need one image for the initial process and then another image for the final image that goes to that gets deployed. Okay. Did that answer your question? Okay. Would you like to ask your second question?
Sure. Well, my other question was whether the first stage gets stored as a separate image.
It definitely does.
Images.
It does.
So we can basically then reference it in a different Docker file as well?
Well, it definitely does. But I guess that's true for almost for any instruction. So these intermediate stages, like inside a stage, these intermediate images, they also get stored somewhere. When you type, let's go here, for example, and type Docker images. So I don't see most of these intermediate images. I see only the ones that I created or downloaded, but they're still here. That's why when I cleaned the cache, I had to invoke to execute Docker builder prune, because the builder itself has a cache, and it caches some of these intermediate images that are created from these simple instructions. But definitely, when I have a whole stage, that also gets stored. So the answer is definitely yes.
Awesome. Thank you.
Sure. Any other question, guys?
This is Tom Dietrich.
Hey, Tom.
Thing you were suggesting using the Alpine. How do we know that which ones of those systems are okay for security? I mean, I don't know much about Alpine.
Okay. Well, these first of all, we have tools that we use. We have Veracode, and these images can get scanned, and we'll know if there are any vulnerabilities that are related to these images. For example, if we're using an old Alpine that has some security vulnerability, and we'll know that we need to upgrade. And that's important to have as part of your pipeline, scanning these images. Additionally, all these images, especially official repositories on Docker Hub, get scanned with Snyk, SNYK. So you can see reports regarding that as well. So this is addressed regularly and for all public, let's say well-known public images. Sure, if you take like any image, any random image that someone pushed to Docker Hub, that could be a security risk. But if you take the well-known images, you're pretty safe there. And still, you have to incorporate checks into your pipeline. Okay, guys. So thank you very much for joining me. And I hope to see you soon in my next session. Bye-bye.
Thank you.